Now I want to look at the limits of a sequence. Okay. So when we're talking about finding the limit of an infinite sequence, it's a lot easier than it is to find what a infinite series converges to, for example, where we're actually adding the terms. For the sequence, we're just looking for, okay, what number is the sequence going to, if any number? So this is just basically just the regular old definition of the limit applied to a sequence. Okay. So if a sequence, so if we say sequence a sub n, and we might just write it like this, we might not put the bounds on there if it's clear on the context. If a sequence a sub n becomes arbitrarily close to a finite number L as n becomes sufficiently large then we say a sub n is a convergent sequence. Okay, so we're using the same language as the improper integrals. And L is the limit of the sequence. Okay. So then we write that the limit as n goes to infinity of a sub n is equal to L. Okay. So, and this is literally what we do. We just take the limit as n goes to infinity. So it's just like taking any other infinite limit. If a sub n, sequence a sub n is not convergent, we say it is divergent. Okay. Meaning that it's going to go to infinity at some point, or negative infinity. So just as some examples, so we can go back up and look at the ones that we already looked at, for example. So I'll start at the, let's see what the first one we did was, and I talked about it a little bit, right? But this first one right here, a sub n, if we take the limit as n goes to infinity, the negative one is going to keep it from converging. If we just look at the n over n plus 1 part, it's going to go to 1. But the negative one is going to make it continuously flip-flop between positive and negative. So it's not arbitrarily getting closer to one particular number. It's arbitrarily getting closer to -1 or 1, depending on where you're looking, right? So in this case, we would not say that it's convergent. This one right here, 3 to the n over 3n plus 1, this one we also would not be able to say is convergent. So it might take a little bit of math to actually show this. And I guess we can actually do it. So if we take the limit as n goes to infinity here, we would get 3 to the infinity over 3 infinity plus 1, right? So we get infinity over infinity. So we can use L'Hopital's rule here to say that this is the limit as n goes to infinity of 3 to the n times natural log of 3 over 3. So the natural log of 3 over 3 doesn't really matter. What matters is that 3 to the n is still going to infinity. So this is going to be equal to infinity, right? So this is not converging to a finite number. So we'd say that this is divergent. This one, same thing. When it's negative, like when there's a negative flip-flop in here, we can't really say that it's converging to anything. If we ignore that part, if we just looked at the 1 over 2n plus 3, that would definitely be converging to 0, right? Because the limit as n goes to infinity, there would be 0. So this one's an interesting one. The 2 to the negative 1/3 to the n. Okay. So this one's a bit of an interesting case because while the negative flip-flop is here, right, where it's flip-flopping between positive and negative terms, we can see that they are, these terms are getting very small. And in fact, they're going to 0. So if you're alternating between negative and a positive number, but you're getting closer and closer to 0 where the sign isn't going to matter, you still could converge to 0, right? And this one in particular does converge to 0 still. So if we took the limit as n goes to infinity here, this would indeed go to 0. It's a little bit tricky to show here, so we'll save that for when we talk about when we just talk about geometric sequences. Okay. For now, let's look at a few different examples. We look at 1 minus 1/2 to the n. Okay. This one's a little bit easier to see. So if we take the limit as n goes to infinity here, okay, so first of all, the limit of the 1 part is just going to be 1. So we're really just taking the limit as n goes to infinity of 1/2 to the n. So there's a few different ways you could think about this. First of all, I mean, I guess the easiest way to think about this is that 1 to the n is just going to be 1 because n represents a positive integer. So this is really just the limit as n goes to infinity of 1 over 2 to the n. So this is 2 to the n is going to infinity, but it's in the denominator. So this whole thing is going to 0. So ultimately, this limit is just going to be 1. Okay. And this is why, in general, that geometric sequences do converge to 0. Because if you notice, just this part alone is a geometric sequence. It's just a little bit trickier to show with that negative in there. But we can see it a lot more easily if there's just a positive number in here. And I guess maybe now's a good time to look at the negative version of this, I guess, instead of waiting for the geometric series. So let's just look at this one in particular. Let's look at negative 1/2 to the n power. And you could use this and prove the geometric sequence we were looking at earlier. So we want to prove this using the squeeze theorem, which was a limit theorem that we did talk about in Math Tools 1, but we kind of glossed over it a little bit because it wasn't really relevant to any of the limits we were looking at the time, because it mostly is just used in trig, which we weren't really paying much attention to, but it is useful here now that we're looking at sequences. So this idea that it flip-flops between the positive and negative numbers, we can write that using inequalities, right? Negative 1/2 to the n, this is less than or equal to 1 over 2 to the n, which would be the positive version of it, and negative 1 over 2 to the n, which would be the negative version of it. So the squeeze theorem tells us that we could take the limit as n goes to infinity of basically each of these parts individually, and really we're taking the limit as n goes to infinity of the left side of this inequality and the right side of the inequality, and then if those are the same number, that tells us that the middle of the inequality also goes to the same number. So negative 1 over 2 to the n, that negative on the outside isn't changing the logic that we used for this problem up here, right? So this is still going to 0. Okay, and this is another way to write limits, by the way, which I don't think I've used. You could just write the arrow to what number it's going to. So you'll see that pretty commonly in this context. And then 1 over 2 to the n is also going to 0. Okay, so this is going to 0. This is going to 0. So that tells us that the limit as n goes to infinity of this is less than or equal to 0 and greater than or equal to 0, meaning that it must be equal to 0. Okay. So the limit as n goes to infinity of negative 1/2 to the n is indeed equal to 0. So, and we can use the same logic for any geometric sequence, whether there's a positive or a negative number in the middle there.